Welcome, everyone. It's my pleasure to introduce Mauricio Gamonal, who will be telling us about primordial power spectrum in effective theories of inflation. Mauricio, please.
Well, thank you very much. Hello, everyone. First of all, I would like to thank the organizing committee for this kind invitation. I am truly grateful for the consideration. Um, Today, I am excited to share some recent results that we obtained together with my advisor, Eugenio Bianchi, in the context of primordial cosmology and generally the phenomenology of quantum gravity. These findings are based on two papers, that the most recent of which hopefully will appear soon in the archive, probably later this week. So let me start from some phenomenological aspects first, and which is the main quantity of this talk. It is a fact that we have measured the cosmic microwave background to great precision, and the temperature fluctuations in the macro in the CMB. These fluctuations are encoded in this coefficient, the CL, that you can see there, as a multiple expansion. And on the right, we have seen what has been measured. These are the data points coming from the temperature fluctuations of the power spectrum. So the CMB physics, that is to say the acoustic oscillations and the decoupling of photons from matter, is captured by a transfer function. And the rest of information is encoded in what we call the power spectrum of curvature fluctuations. So why this is important for us? Let me take this picture. In the horizontal axis, we have the number of refoldings, the logarithm of the scale factor. And the vertical axis, we have the comoving scales, or 1 over the Hubble radius. And we have here us, the Earth, measuring 13 billion years after the CMB, the information coming from the CMB, the radiation coming from the CMB. Kmax and Kmin represents the range of observable modes that we have available from Earth. And the standard cosmological scenario, the standard cosmological model, is well described after the hot Big Bang. Why this is important for us is because the power spectrum that we observe in the CMB can have a primordial origin, as it happens, for example, in the context of cosmic inflation, where an epoch of an accelerated expansion before the hot Big Bang allows vacuum quantum fluctuations of a field, scalar field, or any kind of field, any field, to be imprinted in the CMB at later times, providing in this way the seeds for the large-scale structure of the universe. So in this picture, a natural question arises, and is the following: can quantum gravity regime, the regime that we expect to be described, for example, by quantum gravity, by spin forms, or any formalism, can have some imprints that, in principle, can be observed in the CMB, for example. This is a fundamental question. This is something that has been discussed in detail, particularly in the LQC community in loop quantum cosmology, and it's a fundamental question. We would like to have an answer to that question. So the approach that we follow is slightly different in that sense. What we want is to push as much as we can the quantum field theory regime, developing in this way useful tools and techniques that we can use to study for the transition period between the quantum gravity regime and the quantum field theory regime in the most precise ways, in the most general way. That is the logic we are going to follow. So The primordial power spectrum of curvature fluctuations is what we see here. This is the same plot as the one we had before, with the ripples removed. So it's the primordial power spectrum. And this is a reconstruction from Planck 2018 data, showing an almost perfect power law in this region that we can see here. That is usually characterized in this way, is parameterized by an amplitude and a tilt, ns, that has been measured with great precision. Although this is a simple ansatz motivated by inflation, for example, deviations from the power law can also be present in general. And if you have a particular model, you can even predict what are these deviations. So if NS represents the slope of the power spectrum, deviations from the exact power law can be characterized by two quantities, alpha and beta. These are the running and the running of the running of the scalar tilt, and represents in a way the second and third log derivatives. So if you want a very simple understanding, this is kind of doing an expansion around a pivot scale, K star. And as the first approximation is just the tangent, but you can improve that. But to improve it, you need to go to further and further extension parameters. Yeah, you're going to be first order, second order, and so on. So on the right, we have some examples. Blue represents a negative running, negative alpha and 0 beta. Red represents negative alpha, negative beta. The values are a little bit exaggerated for illustrative purposes, but you can see that different at scales very far away from the pivot scale, that is the one usually used in Planck, for example, there are deviations that might be considerable. So the idea here is to obtain model-independent analytical expressions for these quantities, for alpha and beta, for the runnings, which is it's a non-trivial calculation. So what we did is try to develop a framework in the most general way with the available tools that we have today. And this is the outline of what this talk will be about. First, we are going to introduce this framework. It's a general framework to contain two ingredients. It contains two ingredients. One is very precise. So we study the power spectrum at what we call the next to leading order, N3LO. And also it's very general. We are going to see that it's applicable to a large and wide family of effective theories of inflation. And the second part, we're going to study some particular models motivated by the logic of considering inflation as a purely gravitational phenomenon. That is what we would like to see. And in the third part, we are going to discuss some preliminary results that we've obtained very recently about the possible pre-inflationary epoch and the squeeze vacuum states, the vacuum states that are basically non-Banch Davis vacuum.
Could you explain the symbols, like what is psi star, what is psi, and what is all these p's and so on?
Yes, I will explain each part of this formula. The formula that I have in the top is the genetic result, but I'm going to introduce that just in the next slide.
Okay.
Thank you. So let me introduce with the ingredients. What we do, where do we start? First, we need an action. We are considering the standard QFT procedure in considering fluctuations around a classical background. So for that, we need a gravitational action. The action can contain matter fields as in a standard single field inflation, but is not required, and we are going to study models that actually don't require an inflaton field, for example. But in the most general case, we can have a matter field, some scalar field if you want. The second ingredient, we are doing small perturbations. We are going to consider first a flat Friedmann-Lemaitre-Robertson-Walker background, where we can do Fourier transform and do standard cosmological perturbations. Once we do it at quadratic order, we see that in general, we can do a scalar vector tensor decomposition. And each of these modes, the SVT modes, we can study them since they decouple, we can study by each of them independently. So for now, psi could represent curvature fluctuations, curvature perturbations, or tensor modes, or in a more general theory, we can describe other kind of modes. The important part of this is that once we do small perturbations, we take these fields. The quadratic contribution to the action of these fields can be written in a very general way in this form. As we can see here, it contains the standard scale factor that in the case of a single field scalar single field inflation, it's a particular case of this scenario in which the kinetic amplitude for scalar modes is just epsilon, for tensor modes is just constant, and the speed of sound is 1 for each of these two modes. However, if we have a more general theory in which these coefficients, these functions are completely different and independent between each other, we may find very interesting features, and we can do a study. Once you have the model, then we can produce these quantities, particularly in our spectrum. We work with one particular set of assumptions. We assume that this kinetic amplitude and the speed of sound only depend on time, according to isotropy and homogeneity of the background, and they don't depend on the modes. So that allows to study a large wider family of effective theories of inflation, as we can see in the next.
Sorry, can I just ask a quick question? In your previous
Sure.
slide, you say matter optional. You just mean fluctuations, right? Otherwise, what is the scalar? What is the scalar degree?
Yeah, that is a great question. I will mention in the part 2 one example of a theory that has a scalar degree of freedom, but it's only a gravitational one. Starobinsky inflation is that particular example in which.
So it's not Einstein gravity. That's what
it's not Einstein gravity, exactly.
Okay.
So it's a gravitational action, but not necessarily Einstein Hilbert. That is
Okay.
a very good point. Yes.
Thank
you. Okay. So let's go ahead. We have a third part of the ingredients, which is an expansion, Hubble law expansion. So in the case of cosmology, we have the Hubble rate, that's h. It's the ratio between the time derivative of the scale factor divided by the scale factor. And we can see that an accelerated expansion, a phase of accelerated expansion, is characterized by having this epsilon defined here as the derivative of h with respect to h squared to be less than 1. During the inflationary epoch, particularly at the pivot scale in which Planck does the most precise measurements, we expect this quantity to be very, very small, not only less than 1, but actually much less than 1. So we can extend this Hubble flow parameter to the other quantities, to the kinetic amplitude and to the speed of sound. So we extend this is what we call the Hubble flow expansion. And when we talk about M3LO, we mean that we are considering all the contributions up to epsilon squared for each of these epsilons. So you can see from the quadratic action, each of these coupling contributes to the Hubble flow expansion. We can see that this particular class of theories, this family of theories, applies to a large amount of models. Single field is the particular case, is the simplest one, but it's not the only one. There are theories like F of R theories. Kinetic inflation fits within these kind of theories. LQC also in a particular prescription one may be considering as part of this this kind of prescription, this kind of family. Gauss-Bonnet coupling with scalars and so on. We can do a whole classification of models, and a lot of them fit within this this family of theories. Except from those that are, for example, parity violating, like Chern-Simons theories, that some inflaton field coupling with Chern-Simons term, because in that case, the kinetic amplitude and the speed of sound depend on the mode. So we are not describing those theories, although in principle one may be able to extend this framework to those models. All right. So
can I ask you another question quickly, which is,
sure.
So what is, so the things that are not covered, so for instance, if I think of an ultra slow roll phase where one of the slow roll parameters is large, that's not going to be covered by this formula also, isn't it?
Sorry, can you repeat the question?
So if I consider an ultra slow roll phase of inflation where one of the slow roll parameters is large and is not small, that's also not going to be covered by what you're saying. So is that not correct?
So it will depend. When we say this is a small, of course, if it is very, very small, only the first order, the one that is usually studied, captures a lot of the physics. But once you go to third order, even if these epsilons are slightly not that small, but still less than one, for example, this framework can capture way more than the usual standard formalism of the slow roll approximation, for example. So I'm
just wondering, so if I have, for instance, like this tachyonic models where you are expanding not around some, I mean, the flat potential is around some maximum, then what you can have is that one of the slow roll parameters, maybe what is usually called eta, I don't know exactly what it means in terms of these quantities, that can become large, that can be like an order 1 now. So I'm guessing for those kind of models, this is not going to be a good approximation. I mean, those are not necessarily more interesting models. I just want to know if they are covered by this formalism.
Yes, I agree. And like,
okay,
if it goes order 1, then it's likely that their approximation will not tell the whole picture. Yes.
Thank
you. All right. So what is the technique we are going to use? We have 2-point correlation functions from the CMB. We use the standard Fock representation of the fields with these SVT modes can be quantized in the standard sense. And we study fluctuations around a vacuum state that we are going to consider for this part of the talk to be the quasi-Bunch Davis vacuum. This mode is represented, the power spectrum will be basically the absolute value squared of these modes. And we use the standard Mukhanov-Sasaki trick via time reparametrization. So we have a new time variable that is just a minus k tau, where tau is a generalized version of the conformal time. And the important point of this expansion is that what is usually done in the literature is taking the epsilons, the Hubble flow parameters, to be constant. We are going to give it some time evolution, so we are not going to assume they are constant. We can expand it around this time, and that is what we're going to give us N2LO and N3LO corrections. What we see here is the equation of the mode equation that, if we do this reparametrization, takes this very simple form. and where the G is a function that contains all the information coming from the model, the particular model. So all the epsilons are in this G1, G2, and G3. And this is a very important point. So at leading order, when all the epsilons are 0, we have just Bunch-Davies, exact Bunch-Davies. This is exact de Sitter, and we can solve it exactly. If we do NLO, that is to say, we consider only the first correction. We consider the epsilons to be constant, very small and constant. Then we can still solve it exactly, and we are going to find some particular combinations of Bessel functions. But once you have the first correction, N2LO, and so on, an exact analytical solution is not available. It's a very, very hard, complicated function. And so then the question is, how do we proceed? How do we go? And that is the technique we are going to use, and the framework that we're going to use is based on Green's function method that was introduced 23 years ago. And it's based on the following. Once we have a mode equation for each of these modes, and the Gronskan condition coming from the canonical commutation relations, we can introduce the Green's function, and we are going to find an order by order correction around the exact Bunch-Davies vacuum. This gives us the quasi-Bunch-Davies vacuum state given by this particular formula, when you can see that all the physics is encoded in this function G. So we have to integrate this in a recursive formula in such a way that we obtain these corrections, W1, W2, and W3. Once we have the full W, the quasi-Bunch-Davies vacuum, we can compute the late time power spectrum. That is the power spectrum for the frozen modes at the once the modes are frozen. And it's just this combination here that we can compute directly. The results is the formula that we saw at the beginning. We have the first part, this first contribution. H is the Hubble parameter evaluated at this pivot scale. So we are going to evaluate this power spectrum around a particular pivot scale in order to make contact with observations. We have the speed of sound Q here, and this function kinetic amplitude. All of these quantities evaluated at the pivot scale, and each of these P0, P1, P2, and P3 are very, very hard coefficients, particularly P0 and P1. But the important point of this, you can find it in the paper, the exact expressions, is that this gives us the N3LO corrections, right? This gives this quantity starts at epsilon, P1 it starts at epsilon, so the first one gives us something like a power law. But this will give us the running, which is the log derivative, the log derivative, and the running of the running, beta, which is the log derivative of the power spectrum. So I'm not going to show you.
Can I ask a question here?
Sure.
If you just go back, I don't understand your state. So can you just say, yeah. So normally one would just say that I got Bunch-Davies vacuum at the onset of inflation, but you're now saying that even at the onset of inflation, the vacuum is not Bunch-Davies? Or are you saying that because of dynamics, is no? What exactly is being said here? Are you looking at Heisenberg state and you're saying that you've got a different state, which is not Bunch-Davies? Is that what you're saying throughout?
No. I mean, what this means is that the vacuum at the onset of inflation is not exactly Bunch-Davies, and it's a quasi-Bunch-Davies vacuum. So it's this whole combination here.
Right.
And
but I still don't understand what the principle was to select it. Bunch-Davies is selected by the symmetries. So quasi-local now you don't have symmetries, or those are broken. So I didn't understand the Green's function idea to select it. What is the principle which selects this quasi-Bunch-Davies vacuum?
So in terms of physical principle, it is true that it's not a vacuum that is invariant under exact de Sitter and all
or
the
anything,
things that
but
we
what
have.
is the principle?
Yes. So this approach is, I would say, is a phenomenological approach in the sense that it's very unlikely that that there's a physical principle that can give us a slightly deviated version of quasi-Bunch Davis, but it's what is very consistent with observations currently. At the last part of the talk, we are going to see how a different original state, a different initial state, can then take a limit in which we can study this quasi-Bunch Davis vacuum state in a more general way. That is the squeeze backward that we are going to discuss further. But I agree. In terms of physical principle, in a simple physical principle, I'm not sure I can give you a prescription that could characterize a vacuum state of this form. As you say, these corrections are encodes dynamics, it encodes part of the models and the physics that is in that epoch, that regime of the universe. So it's not a vacuum that depends only on. So let me go again. So if a Bunch Davis vacuum is the preferred vacuum, if you want, for de Sitter, for exact de Sitter, if you have a different background, of different, you don't have exact de Sitter, you have quasi de Sitter, then you cannot choose. Bunch Davis is no longer the right answer for that particular specific background. So this is a way to adapt to a background that is not exactly de Sitter, but a slightly different version of de Sitter.
Can I add something?
Hmm?
Can you hear me? You're muted. Is it working?
Yeah, I listened.
Yeah.
I listened to it.
Good. So I just wanted to add something because this question is important. This question I was asking about what's the physical principle that selects this state. So one thing that I can add is if in the asymptotic past the background approaches de Sitter, that is, if the epsilons go to 0 in the asymptotic past minus infinity, then one has a clear notion of a clear physical principle. Take the in vacuum in Bunch Davis. And this technique using retarded Green functions just takes in Bunch Davis and evolves it order by order in these slow roll parameters. So it's a way of starting with Bunch Davis as initial conditions for the mode functions of Bunch Davis. And these initial conditions are taken as an in vacuum. Then there's the separate physical question of what is a good state for inflation. This one, I would say, it's selected by the fact that it approaches Bunch Davis in the far past.
Okay, thank you. I think we should go on. We can come back to this.
Can I just say one sentence here, which is, do you agree that maybe another way of stating the physical principle here is that inflation has a finite starting point, so you cannot push this back to minus infinity. So you cannot. So whenever inflation starts, I mean, it's very far deep in the past, but it's like starts at some finite time which is 0. So that's a way of saying what Eugene was saying, that epsilon doesn't go to 0 if I go back to put my initial conditions. If I put my initial conditions at some finite time in the past, then that would not be Bunch Davis states, at least not for all modes. Maybe for observable modes, it can be effectively Bunch Davis.
I agree it won't be Bunch Davis, but I mean, why should it be this one? That's not, I agree.
I think it's an expansion, right? Around like the epsilon equal to constant. So it's just like a expansion around the Bunch Davis.
I mean, what does this expansion achieve? I mean, you are de Sitter invariance. Now what is it replaced by? There should be something, right? Like it minimizes energy at some stage, or it does something else. I mean, okay. Well, I think we should just go on because then we can come back.
Yes.
Okay. Thank you. All right. So I'm not gonna show you these ugly formulas. But just to point out that as you can see, the information is encoded in HC and C. So we have all these very precise expressions for each of this quantity, the tilt, the running, and the running of the running. So let me now introduce the second part of the talk, which is using these techniques to something that I think is interesting. This question is, can we describe the inflationary epoch as a purely gravitational phenomenon? Because the spirit of having a scalar field with some particular interactions that is usually in the literature of inflation is might not be the right picture at all. I don't know. But then if that is the statement, and we may ask, what is the simplest model exhibiting this characteristic that remains consistent with these observational constraints? And Starobinsky is one of these, probably the simplest one. So I want to emphasize this. This theory, this model, is not a fundamental theory, but it's a sector of semi-classical gravity and in the spirit of effective field theory. And we can study without doing this usual field definition and conformal transformation of the metric to each other. We can study directly on the physical metric and directly on the geometric frame that we call. We see that, for example, it has a modified Friedman equation that contains these terms here. And if we solve this equation, we can notice that Starobinsky has included in itself a phase of what we can interpret as a inflationary phase. You can see the derivative of h in the vertical axis is almost constant, but is still changing a little bit on time, and is what we can study as a particular realization of this framework. This is a purely geometrical model, so all the quantities are quantities from geometry. It contains a physical scale, the coupling alpha. It's a very large number, and it has an approximate behavior. The scale factor, for example, behaves as an exponential, but with some particular correction. So it's not exact de Sitter, it's quasi de Sitter by almost construction. And this is the Ricci scalar for this particular model. So once you do Starobinsky, you can do perturbation theory around it. You will have two tensor modes coming from the standard Einstein-Hilbert action, and there's one scalar degree of freedom coming from the quadratic term. So again, no conformal transformation. We are just using the physical metric of this model. And we can find the kinetic amplitude and the tensor amplitude for is the kinetic tensor mode. And as you can see, they're functions of chi, and chi is a function of the background itself. So it's a pure geometrical model that can give us quadratic contributions to the action. So it has an imprint on the CMB. This in principle is simple to solve at leading order using the standard techniques, even at next to leading order, but it's highly non-trivial at N2LO and beyond. That's what we have to use this framework. So what we obtain at the end is we compute the amplitude, we compute the whole calculation of the power spectrum, and we found something that is very, very interesting. That is the next to the N3LO correction corrects the tensor to scalar ratio, to is the amplitude of tensor modes divided by the amplitude of scalar modes. And this correction is not small, it's around 7% of the original standard correction. We found it in terms of the number of refoldings, but we noticed that we can write it in terms of another observable, which is the scalar spectral index. In this plot, we have R, tensor to scalar ratio, on the vertical axis, and the horizontal axis, NS. And we see that the deviation is slightly, it's very little, but it might be important and relevant for future experiments of cosmological observables, Lightbird, for example. This orange region here is a forecast from this experiment. This is based on Japan, and is assuming a fiducial value of R with the experimental precision that they expect to have. So the blue and the gray lines regions, they represent the current Planck and bicep Keck constraints on inflation. So we obtain this correction is kind of surprising because it's not small. It's actually slightly large. It's 7%. We also found particular predictions from Starobinsky.
Can I ask a question?
Sure.
Yeah, hi. So, I mean, Starobinsky inflation is like 40, 50 years old now, right? I mean, it's an old theory, right? I guess my question is that, like, are you the first group to study the tensor perturbations of Starobinsky, of the Starobinsky action? Like,
definitely not
has
the
this
first
not
one.
Right.
Definitely not the first one to study Starobinsky, as you say, it's very old model.
No, the
But
tensor perturbations, because because that would be the natural thing to study in the context of inflation, right? The different perturbation. Anyway, so this is just like, I was just asking for a historical clarification. That's what it's.
Sure.
Yes.
So yeah, in the literature, usually, the standard trick of going to conformal transformation and basically writing Starobinsky as a scalar field plus some particular potential is what is in most of the literature. I'm not 100% sure if we are the first one to study in this geometric form. I don't know, but
Okay, thanks.
What I can say for sure is that we are very likely to be the first one to go to N3LO for this for all these effective theories, but in particular for Starobinsky as well. So that is a new thing.
But can you tell us what is the mechanism for this surprisingly large 7% effect coming at third order and one is one, So
yes,
I mean, one would not expect that to happen at third order. So what is it that enhances the effect? So if you go back to the slow roll parameters, then are you saying that for this model, the slow roll parameter is not that slow roll? I mean, where is it coming from? 7%, but when would I expected this to come from the third order correction?
It was surprising for us as well because we didn't expect it. So what I can say about it is that when we do this perturbation, in particular, we can expand in terms of the number of efoldings. So we can convert epsilon 1h, the first Hubble flow parameter, in terms of number of efoldings by definition of number of efoldings. And what we found is that in this expansion, it goes as 1 over n, 1 over n squared, 1 over n cubed, and so on. There are some additional contributions from these corrections that are of the form of log ns over ns squared, log n squared over n s cubed, and so on. And in particular, for the scalar to tensor to scalar ratio, the situation is that the coefficients that is usually done is a large coefficient, comes from a large coefficient by a combination of different contributions. So there are contributions coming from the expansion itself, from the N3LO expansion, and there are contributions from taking this approximation of not approximation, but to write it in terms of the number of efoldings. So we were at first. We thought, okay, this might be an artifact of the number of efoldings expansion. But when we write it in terms of this NS, so in terms of this observable, which is a quantity, so an expression that it's valid for both frames. It's valid either from the working with scalar fields or working in this geometric framework, and it gives exactly the same result. So it's a very robust result.
I'm not worried about that. That equivalence between the two frames. It must come out. But I'm still surprised in any frame. Why should there be this 7% effect? So what is it that something is counterintuitive here, right? So something that people had missed. I mean, everybody thought this effect would be much smaller. So what is it that people have been missing? I would like to.
Yeah, I can only speculate in this for the physical mechanism. If you ask for why these contributions are not smaller or much smaller, it might be possible to the fact that Starobinsky inflation in itself is already a truncation of semi-classical gravity. That maybe it has some contributions that are not considered yet. And that is a possibility I could see in principle. To check that, that will require further research, I guess.
Okay, thank you.
Can I add a technical point to this question about what was missed? I think there's something specific that was missed when people computed R, this tensor to scalar ratio for Starobinsky. They found 12 over n squared. And the expectation is that if you go to the next order, you get something like 1 over n cubed. And n cubed is much larger than n squared, and so you can neglect it. What was missed is that first, if it's something over n cubed, you need to know the coefficient. And Mauricio computed the coefficient. The coefficient is 24 over n cubed, and then it's just 55. So this is non-negligible. And second, there's an additional term that is minus log n over n cubed. And this is also non-negligible. So now there's a cancellation between the two. So at this N3 LO, what remains is 7%. And as nobody had gone to N3 LO, nobody had seen these two terms. This seems to me that is what technically was missed. This is an expansion, is robust for n large. But after all, n is 50, 55, 60. So we should take care of these higher orders.
Right. So you're saying that it is one thing to say something goes like 1 upon n squared and cube, but the question is, what is the coefficient? And people had implicitly assumed that the coefficient was of the order of 1 everywhere. And this just is not right. So this is what your key point that you have found. Is that correct?
That's correct.
Okay, thank you. That helps a lot.
All right.
So, sorry, can I just also ask a question again, which is, maybe I missed something that you said. So when you have these initial conditions which are not exactly Bunch-Davies, do you have any additional parameters, or like when you compute this correction, what do you have to put in? Like, is there nothing else going into the theory?
Yes, that is one of the nice things about Starobinsky. The only thing that it depends is this coupling alpha is the only parameter coming from the model, and then to describe this whole expansion, there is one family.
No,
parameter
that I agree. So
depends on
that's
n.
the standard Starobinsky, but there is no additional parameter coming from your initial condition. Is that the statement?
Not now, not in this stage, because as I said, the quasi-Bunch-Davies vacuum only contains information from the background. And if the background is described by Starobinsky, and Starobinsky only have one parameter, then there's all we can have. Now, in the third part of the talk, if we can discuss,
when you go to squeeze, there will be another. Yeah, I agree. But then my second question would be: so you found this 7% discrepancy with the standard result when you go to third order, but what happens to the slow roll parameters themselves? Because those are presumably also getting corrected because of these same effects. Epsilon and eta, are they getting also like 7 or 10% correction? And if yes, then that would also, those are also significant. Or is there some reason why they are not getting corrected, but only the tensor to scalar ratio is getting corrected?
So the Hubble flow parameters are defined once and for all from the background. It's just standard definition. So that's one important thing. We don't define it in terms of the potential, but we define it in terms of these quantities, Z and CT. It depends on the background. What I can say is that the epsilons, if you expand it in terms of NS, what people usually do in the literature is that epsilon goes as 1 over 2 NS, number of foldings, N star. if you want to go and be consistent with this expansion, you need to go to N3LO. So you will also
right.
have corrections of order 1n squared, 1 on n cube, and so on. So yeah, in that sense, that particular expression, that relation is not
because
exactly
that would be important for the background resolution, right? Because it means that if epsilon, for instance, becomes 10% larger, then we should be able to trust like slow roll expansion or trust the background quasi-distributor only 10% less of the time or something.
I agree. During the inflationary phase is control is less than 1, the epsilons, at least at this order.
Okay.
There are other predictions that Starobinsky makes, and because of this is because it has only one parameter. All these quantities at farther and farther order are completely predicted. They are not. We don't need to constrain parameters. It's just a prediction, so it can be tested against observations. This is the deviation from exact consistency condition. It's an N3LO contribution, so it is not exactly the same. And it's very small, but in particular could be improved, for example, by observations of LIGO and in combinations with Planck and other observations. And as well, scalar running, this is also important. There is a negative running that Starobinsky predicts. And we confirm, at least at this order, that is still running, so it's still negative, as we can see here, which is consistent with current constraints. They are not very good constraints, but it's most very likely that they will be improved in the next few years. So it's also an important point to have. Here, alpha, don't confuse it with the coupling of Starobinsky. They are different. I think this is the running of the tilt. So we have done this for Starobinsky, and just to make sure we're good with the time, let me start now the part 3, which is as we mentioned, we started using this quasi-Banach Davis vacuum, but what if the initial conditions were not exactly this quasi-Banach Davis vacuum? We don't know the physics, we don't know the mechanism, and I think that is the challenge for all of us to find physical mechanisms, physical prescription to give right or physically motivated initial conditions. This is something that has been, and I'm aware that has been explored in the ILQGS community. I'm not completely familiar with the techniques and methods, but it's something I am aware is a very important thing. And also, there are efforts in the observational community to identify these features in the power spectrum. So on the left, you have a paragraph from Planck, constraints on inflation. And on the right, we have a paragraph from the Euclid experiment this year. And it's something that these large experiments, they are trying to find very actively deviations that are not just the tiny little deviations from the power law, just running or running over running, but huge deviations or bigger deviations than that, or different kind of deviations from that. So then the question is, can we apply this framework that we used to this kind of theories, of this kind of picture? So we use the standard procedure, that is, we have this quasi-Banach Davis vacuum, and we do a Bogoliubov transformation in the Fock representation of the creation and annihilation operators. And basically, the point is that if the original quasi-Banach Davis vacuum is a basis of solutions that satisfy the solutions of the mode equation, we can write a linear combination of this W tilde with 2 parameters, alpha and beta, that depends on the mode K, in such a way that it represents a new vacuum state as long as preserves the Wronskian condition of the vacuum. So they need to satisfy this particular equation. This is what we call a squeeze state. And in the literature is the standard expression that is almost everywhere is that the power spectrum for this kind of initial conditions, this can set initial conditions different from Bunch-Davis or quasi-Bunch-Davis, is of the form alpha minus beta module squared, the standard quasi-Bunch-Davis vacuum. So the question is this still true next to leading order or n to LO and so on? And we find a negative answer for that. So let me go here. Let's define U epsilon as the ratio between the squeezed power divided by the quasi-Bunch-Davis power. So this is what we expect to be alpha minus beta module squared. We can expand it and we can write it in this way. And we find here that W star, the complex conjugate of the mode, the quasi-Bunch-Davis mode, divided by W, induces a phase on this squeezing factor that in principle is a generic feature and is present at all orders. We can compute it order by order using this Green's function method, but generically it's there. And we computed. What we found is that this phase, this delta induced by this expansion, it is a very complicated function. It depends on the G's that contains information from the background, and it at leading order it basically goes as ns minus 1. So it's a small quantity. These are all small quantities, but they are not necessarily zero. They are not exactly zero. And this is something that we could explore with more detail. And to give an example of this, and I want to be clear, this is an illustrative example. It might be pathological in the physical sense, so don't take it seriously, but it's just to illustrate this situation. So suppose you have initial conditions that are set at finite time in the past. So we are not setting Bunch-Davis into infinite past. We are setting at some point in the past, some characterized by some time. This might define a cutoff scale related to this time. And let's suppose we have a transition that we have been caused in the past, and then this state, some physical mechanism excites the state and makes it a squeeze state at this time. So we impose these two conditions, and what we find is some Bogoliubov transform, the Bogoliubov coefficients alpha and beta are of this form. This is something that has been explored in the literature in other contexts, but we are going to use it just for illustrative purposes. And what we find is that if you have the exact power law and this alpha minus beta module squared, that is the standard prescription, the standard formula that is used, we have the blue dashed line here. And if you have a N2LO squeeze vacuum, so the formula that we derived, plus some fiducial values for the epsilons, we are assuming a large running to illustrate the parabola feature of the power spectrum. We see there are some deviations that are non-trivial. Non-trivial to calculate and non-trivial to see for observations. It might be important at some point. Then, if you want to study a more realistic values, in principle, we can choose Starobinsky. The epsilons coming from Starobinsky evaluated at the pivot scale, the standard pivot scale. And we see that this is a comparison. It's a log-log plot. The squeeze state, it contains these features, these oscillatory features, and converge exactly to what is the standard quasi-Bunch-Davis solution at large K. You can see in blue here that this is only the running, this N2LO version of the power spectrum with this small running, so it's a small deviation from exact power law. And if you compare the two versions, the two formulas for the power for the two squeeze power spectrum, there are some deviations, particularly for for very small scales, very small modes. And this deviation is it might induce a very small shift in the phase. So why this is valuable? There are many reasons for that, but the important, or probably the principal one, is this is a framework. This whole framework that we developed is very valuable for parameter estimation in cosmological observation. So people can use these parameters, and once you have a model, once you have a quadratic action, you can pretty much straightforwardly use this framework to do parameter estimations of the power spectrum. So with this, I will give the conclusions of the talk. We computed the primordial power spectrum up to N3LO for a wide family of effective theories of inflation. We found these non-trivial corrections to Starobinsky as one of the realizations of this framework. I presented these results at Loops, and I received some comments and suggestions. One of them was checking the results that are valid in both frames, which is something we did. Is this result that I show in terms of the spectral index. And the second suggestion was, well, we did this first for this quasi-Banach Davis vacuum. We would like to do it for a non-Banach Davis vacuum, what we need to do. And we extend these results as I just shown. Of course, the long term is the ambitious one. And this is something that with Eugenio will start focusing. It's exploring the emergence of this squeeze state. If spin films, low quantum gravity, can provide this input for this particular regime on the universe, this could be super important to build this bridge between the quantum gravity regime and the quantum field theory regime as well. So we should prepare and embrace the precision cosmology era that is coming in the future years. So with that's all I have. Thank you for your time.
Thank you, Mauricio. Questions? If people could raise their hands, that would be helpful. Deep.
No, I have a question also.
Okay, well, Abai beat you out slightly, so Abai, go ahead, and then Deepak.
Okay, so I just first of all, I mean, there are proposals, right? Like concrete proposals for the squeeze state for the non-Banach Davis vacuum coming out of quantum gravity era. But those, I mean, they're concrete proposals, and that though they have been used to argue that the anomalies are elevated. So you have those proposals, you could take them. But of course, those proposals did not go to this higher order in the slow roll expansions. And so you could do that. And so you already had that. So I just wanted to say that that is something that is available. My question was really about, I'm not clear about your very last part, because it seemed to me that some kind of a mixture between when you compare things, right? I mean, when you say that you're going to Banach Davis vacuum and another vacuum. Now, if you think of them as a Heisenberg state, then the statement is just going to be that if you use the same dynamics for the field operators, then you will just get the standard relation without the phase factor. Somehow, I think that what you're doing is using the dynamics of field operators with yeah, they're there, right? Exactly. Somehow the dynamics of field operator might be using, in one case, not worrying about expanding the slow roll, or assuming the slow roll parameters are really slow roll and ignoring the corrections, and in the other case, including the corrections. My remark is just the following: that if in fact you have two vacua and you have the same dynamics for the field equations, then the standard relation must just hold. So I think you're in one case you are using this, you are evolving the field operators implicitly somewhere in the framework, using the slow roll parameters which are changing. And in the other case, ignoring those effects. I'm not saying that anything wrong here, but I'm just saying that there's a way to understand the origin of e to the I delta, that there's a mismatch of the way the field operators themselves are evolved in the two cases. That's all. That's the origin of this.
Can I check if I understand your question about it? Are you
Yeah,
saying
please.
that one could reabsorb delta into beta?
Yeah.
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 So good. Yeah, because the perspective that we adopted with Mauricio is that delta is completely determined by the background. And on top of that, this state we are calling quasi-Bunch-Davis, but I guess many would just call it Bunch-Davis. This state is completely determined by the background again. And so alpha and beta are defined in terms of one single special state. So in this sense, we are putting into beta the freedom to choose the state, and in delta only background information.
Yeah,
And the statement that is in the literature that is e to the I delta is just one refers to the fact that mode functions are purely imaginary at late times, but this is true only for this approximation where they are Bessel functions.
No, I don't think that. I think I'm just saying something much more elementary. I mean, I'm just saying that given two Heisenberg states and the same dynamics, given two Heisenberg states which are related to each other by some squeezing, and then, but if that's and the field operators are exactly the same dynamics, then the standard relation just holds. I think you said implicitly that you are separating the two effects by saying that something in the background and something in the state, and I think that. I mean, I'm not saying that this is correct by any means. I'm just saying that from the standard perspective, this is no. I'm not saying that something should be pure imaginary or anything like that, and nothing to do with Bessel functions. I'm just talking about very, very general framework about two complex structures, and just given two complex structures and the same dynamics, then the power spectra with respect to them are related by some formula, and that formula would have, if you like, just one complex number. It's not a. I'm just trying to say that, well, it will be confusing for people, and one might want to say the origin of delta lies because you choose to separate out the state dependence and the dynamics or the background dynamics. We can discuss this later. I don't want to take too much time.
Yeah, but I think this is important point that you are raising because it's about the relations between states, and I think there is a claim here that is already in this paper of 2001 of Gong and Stewart, that is this state that we are using, we are calling quasi-Bunch-Davis. It's a preferred state. It's so that is the thing. That is the physical input that needs to be discussed further. There's a claim that that state is a preferred state. It's not any state.
Yeah. Okay.
Deepak, you had a question next, and then Sudha, I see you're after that.
Yeah, hi. So first of all, I think Eugenio clarified what I was asking, which is that you are indeed, I think, the first people to study this at next to next leading order, right? And that's where you found this
Yes.
this effect, right? Okay, great. Okay. The second thing I wanted to ask is that why stop at R square, right? I mean, why not have an action which is like an exponential of R, divided by m Planck square or something like that? Because it seems to me that if you have inflation and inflation is going for 60 e-foldings, then you would have to go to very, very large order in perturbation theory to take every effect into account, every effect which matters. So okay, that's my question.
Yeah, no, it's a totally fair question, and if I'm being honest, the origin of all this research was study a consistent approach to effective field theory in terms of derivatives of the metric. So if we take the effective field theory approach, is we have Einstein-Hilbert action, the low curvature limit of general relativity, then if you want to, expand around this particular theory, you want to introduce all the possible combinations at, for example, quadratic order in the curvature. So you have R squared, that is one combination. You have a Ricci square and you have Riemann square. These are all the other two simple contributions that you can have, at least assuming diff invariance and assuming preserving parity. You can convert one of these two into a combination of a Weil square term and a Gauss-Bonnet topological term that doesn't contribute to the equation of motion. So in principle, the most general one would be R square and Weil square. And the Weil square, it has some complications because if you take it seriously, it can give you higher order time derivatives that are difficult to implement in terms of time evolution and defining trying to have a well-defined initial value problem. But we try to study that there are some approaches in which you can use it, and that is one of the things we want to do is using some techniques like a reduction of order to try to deal with this in a more consistent way, But yeah, I agree. It's a truncation of the whole. It's just a sector of semi-classical gravity. You can go beyond and beyond and beyond, and eventually you will need all the terms of the Planck regime. But as I said, this the focus here, if we want to connect with observations, is to push as much as we can for all the things that are relevant for the observable quantities that we are going to measure. And in that sense, that is the approach of effective field theory in a way. So assuming that we can measure and observe this at this kind of thing, at this kind of scales, how much can we push the theory that we have in order to find corrections or deviations from the standard general relativity, for example. So I agree, that is one perspective, and is something that should be addressed as well.
Okay, I could ask more, but I'll stop here.
Sudasatwa?
Hi, thanks. Very nice work, thank you. I have two quick questions. One is kind of asking what I was asking earlier. I thought I understood the reason for choosing this kind of states, but I was wrong. So you're not thinking of choosing some sort of state at a finite time, and that's why you get non-bunch Davies, because that would add an additional parameter, which is like when you were starting, like what is the theta? So you're not doing that, but you're saying that even in the asymptotic pass, you don't quite get bunch Davies. You get bunch Davies, but plus some corrections because of having this low roll parameters. But that is so I don't quite understand why is that the case. So for instance, if I think of the short distance behavior of this vacuum, do I not get Minkowski then? Because I would expect that in the asymptotic pass, the short distance behavior should be exactly that of Minkowski space. Or is there some implicit assumption there that the underlying behavior of the underlying physics is not of Minkowski space, like even on short distances? So and if it is not Minkowski, why not? And if it is, why is it? Because you're saying that there are corrections from the bunch Davies, even in the asymptotic.
Yes, so it's a fair question. You can see, for example, from the mode equation here, that in the past, y minus infinity, if you want, no, plus infinity actually, this term vanishes, so you will have pretty much the same mode equations of Minkowski vacuum, and this other term has the functions of log and log square, but in principle also goes and it vanishes at infinity. So that particular set of initial conditions is clear. It's like what you mentioned on the sense of adiabatic conditions for this quasi-bunch Davies is still Minkowski. It's not some slightly different state. Now,
sorry, in fact, I have a quick question there. So I do see from of course, from the mode equation that it vanished, and that's what I was expecting. But from the details of the physics is encoded, where you say that, how do I see that when you take y goes to minus infinity or plus infinity, whatever is your asymptotic path, so you're saying all of these coefficients then vanish, or?
Yeah, like for
is there a
instance,
log y term that worries me?
yeah. Okay, so what I mean is well, what do I have? Yeah, here are the more explicit sense.
Right.
Yeah, they at that time they vanish. They vanish,
Okay.
and so the y is defined here. So
yeah, that's fine.
Yeah,
that's fine.
Yeah. So at minus infinity, tau minus infinity, then it vanishes.
So at tau minus infinity, you still have bunch Davis.
No.
Table
Is
that
Minkowski.
Mauricio asked. Sorry, Mauricio, to interrupt you.
Yeah,
It's
no, go ahead.
that you have at the bottom of page 9. I find it especially helpful because it shows, it gives also names. We are calling bunch Davis only the one that is in exact de Sitter.
Okay.
But then as soon as the background is not exactly de Sitter, you can expand it. So if you look at the NLO, the second line, this one is the familiar one, it's the textbook one. And somehow we learn how to solve it exactly. And we call still bunch Davis the one with Bessel functions, but it's not technically bunch Davis, it's something else. It's taking into account the first deviation from the sitter that we should treat perturbatively, but somehow we are believing in it at every order in perturbations, and we should not, it would be a mistake. So what Gong and Stewart did is to set this as an order by order expansion by using retarded Green functions, assuming that you have these Minkowski-like initial conditions at minus infinity in cosmic time, but taking into account the corrections for the background order by order. So I would say this is a preferred vacuum in the sense that it's the in vacuum. I don't have a good name, a better name for it. We are calling it the background quasi-de Sitter and the state quasi-Bunch Davis. But I think the prescription is completely given by this procedure of expanding order by order.
Right, but then can I not think of this? I don't know the N2LO at all, but for the NLO, it looks like you're just adding like a small mass term, right? This is like the mass term for the inflaton fluctuation or the adiabatic fluctuation, because that is also going to be exactly slow roll suppressed, the kind of term that you're adding. And this is like saying instead of having like a massless scalar field, we know the adiabatic perturbation is almost massless in leading order in slow roll, but then you are doing an expansion of the mass of the adiabatic perturbation in the slow roll parameters. Can I think of it this way?
Yeah, you can think of G1K as a mass that is small, but then the next order is not anymore a mass, it's this mass plus log y, and you actually have to take care of log y. If you forget it, you are not choosing an adiabatic vacuum in the asymptotic past. You would just calculate all conditions in the asymptotic past if you use the NLO instead of N2LO.
Okay, but are we, so maybe this is my last question about this, which is, are you sure that this is, if you do the mass expansion at early times, it doesn't also pick up this kind of logarithmic corrections? I don't know how would the mass of because mass of this adiabatic mode is explicitly determined by the background, as you say. And then if I do expansions in the second order quadratic action, but also keeping the mass to be not a constant and not zero, then maybe this can be, because in that case I don't have to worry about the symmetries, like what I guess Abhay was asking, because in that case it's like saying that, okay, yes, this is the de Sitter background or like quasi de Sitter background, and instead of having just a massless adiabatic perturbation, the adiabatic perturbation we know picks up like a small mass, and these are like corrections for that. But okay, that's just a remark. And then my second very quick related question is, if there are these corrections, so you showed us some plots for the tensor to scalar ratio and things like this, but that would also change. You showed like one plot about the scalar power spectrum for the Starobinsky case, right? Because if the epsilon, as you say, should also be consistently changed, like in terms of this expansion in NS or something like this. So wouldn't that, because you have a plot later on where you show that what is the alpha S, like the rolling of the tilt. Yeah. So something like what you have, this one. So that means that just the scalar spectrum itself is also changed. Okay.
Yeah.
So does this upset the Malus-Sena consistency? That was my second question.
You mean this consistency notation between R and the tilt
Yeah.
of the
Yeah.
tensor? No, it breaks at N3 low. Yes, it's
Okay.
yes. That consistency notation is only a leading order statement that you can make, but it's generally different from zero. That it's not in and we show it actually for single field inflation, for example, that at n is an entry look particular.
Yeah, sorry. I don't mean this one. This one is fine. Yeah, I saw this. I meant like there's a consistency relation for the bispectrum to the power spectrum. I don't know. Maybe you guys haven't looked at it, but that might also be broken by this or not.
Yes, very likely. We didn't do
because
it,
that would answer this question about symmetries, because that consistent relation one can think of as word identities, and if that is broken, then indeed like there's something deep physical going on here, except for just like some expansion in the explorer parameters. Okay, thank you.
I'm sorry, but I think something deep is going on. I mean, now I understand that there's a way to say this, right? Namely that if you are de Sitter, then you can just give the de Sitter modes in the distant past, or as you said, the Minkowski vacuum in the distant past, and then evolve it just as classically. Yeah, you just give yourself some modes and then evolve them. So you define positive frequency modes by going to infinite past, if you like in Minkowski space, and then evolve it, but using de Sitter. And then that is like the Bunch-Davies vacuum. What these people, what Eugenia and Mauricio are doing, are really saying that, well, but let's consider the evolution equation themselves being not de Sitter, but having these corrections from slowly varying, from varying slow roll parameters, which are varying, right, in time. So therefore, your field equation satisfied by the modes itself is changed.
Right.
And therefore, if I put the same boundary condition in the distant past, I still get completely different field modes. So my expansion of the field operators is just different. So this also answers my question about, what is the conceptual meaning of this? The conceptual meaning of this is really, it is a complex structure that is selected by going to the distant past, but on the space of solutions, not of the standard of the modes of the scalar fields of the perturbations, which are propagating on constant slow roll parameter space-time, but on a time-varying parameter space-time. So I think you're just generalizing this prescription, getting a complex structure, unique vacuum on the space of solutions to the field equations that are of physical interest to you, namely the ones for which the slow roll parameters are actually changing in time. So I think it all sort of conceptually seems to tie together.
But if this gives like a 7%, around 10% correction to the tensor to scalar ratio, it might give like a 10% correction to bispectrum, which would be huge for many models.
I agree. So that should be checked. I completely agree.
Excellent discussion. Eureka, earlier you had a hand up. I don't know if your question was lingering.
Oh, thank you, but it has been already answered.
Okay,
Thanks.
wonderful. Were there any other questions? All right. If not, in 2 weeks' time, we have Renata Ferraro speaking on asymptotic safety and canonical gravity. And with that, let's thank Mauricio one more time. Thank you so much.
Thank you very much. Thank you for your time.